Okay, this problem is from AIHL paper 3. Problem number 1 is given 27 marks. You can always pause the video so you can read the problem thoroughly. Okay, for problem number 1, letter A, we have to show that P equals 0.00939. We already know that a period is equal to 2 pi over p. So we'll be using the formula b equals 2 pi over p. But what is the period? From the problem, we can say that since it moves around 669 Martian days, which is equal to 1 year, so that's a complete revolution. So we have 2 pi over b over p is 2 pi over 669. That gives us approximately this answer. Okay, so problem A has been solved. Let's do letter B. Mars completes one rotation on its axis in 24 hours and 40 minutes. So the rotation, complete rotation, is given in hours and minutes. We convert that into hours. So we can see the solution here, and it gives you 74 over 3 hours. The angle through which it rotates on its axis, each hour, is now given by 2 pi, that's a complete rotation, over how many hours? 74 over 3 hours. So that gives us this answer. And this is approximately 0.255, okay, 0.255 radians. Okay, here we go to question number 3. The time of sunrise on Mars depends on the angle delta at which it tilts towards the sun. During the Martian year, the angle varies from negative 440 to 440 radians. The angle omega through which the Mars rotates on its axis from the start of a Martian day to the moment of sunrise at point A is given by this formula or equation. Cosine omega is equal to 0.839 tangent delta, where omega is from 0 to pi. Show that the maximum value is 1.98, correct to 3 significant figures. So if we're going to use this formula, okay, this one, where our angle delta is between negative 440 to 440 radians, we can substitute for this by this one, and that gives us 1.97684, approximately 1.98. So we're able to get this part correct. And then to get the other angle, we substitute the delta, which is 0.440 from here, and that gives us 1.116. So this has been solved. Okay, so for letter D, we have to use our answers in part B and C. So from part B, I put it here, and then at part C, we have the two answers here. Find the maximum value of R of t. So RT max will be the maximum angle. The maximum angle it spins at the start of day to sunrise. This is what we have here. And then the 0.255 is the number of radians it spins in 1 hour. You get it? I repeat. So the maximum of RT, our RT is A sine BT, is we have here 1.98 because according to the problem we have to use our answers in B and C. In letter C, the maximum angle it spins at the start of the day to the sunrise is 1.98. And 0.255 is the number of radians it spins in 1 hour. So if you divide the two, our maximum value for R of t is 7.75. Okay, for the minimum, So the minimum value is 1.16 and it spins 0.255 radians in 1 hour. So that gives us the minimum value of RT is 4.57. Okay, we are now, so we have solved this. Okay, hence, show that A equals to 1.16 correct, 1.6 correct to two significant digits. So we go to our equation here, R of t. R of t is A sine. A is amplitude, right? Or A value, which is computed as the distance between the two values, given two values. In this case, we have maximum minus minimum over 2. So this is the representation, so get 1.6. So this is done. Now the C here, this is our horizontal translation, and C is computed as max plus mini over 2. So translation, we call this our principal axis. Okay, so we have 6.16. For letter G, this is letter G. Find the value of D. Let's go back to the problem. Let S of t be the length of time in hours from start of the Martian day until sunset, given by S of t. The length of time between sunrise and sunset at point A, LT can be modeled. So this is the length of time between sunrise and sunset. This is sunset is S of t, and sunrise could be taken from here until sunrise. Okay. Previously, we have solved for the amplitude, the frequency, and the principal axis, which is equal to 1.6 sine 0.00939t plus 6.16. So if we're going to, so I have here the model or the diagram of sunrise to sunset. So they start at the same day until sunrise and until sunset. So until as from sunrise to sunset could be solved by S of t minus R of t. And S of t is given by this one. And R of t is this. So subtracting the two, you'll have 1.9 minus this. And then 18, this should be minus 6.16 if we remove it from the grouping symbol or from the parenthesis. So this part represent the D here because basically they're the same on these two parts. So D is equal to 18.65 minus 6.16, and that is equal to 12.5. For letter H, let f of t, this one, and hence L of t is the function plus D. And ft could be written in this format, imaginary. So we're using complex functions. Write down c sub 1 and c sub 2 in exponential form. So this will be our c sub 1 and this will be our c sub 2. So c sub 1, recalling a little on complex numbers, we can write it as r cosine plus I sine theta, or rcis. And then we can also write it in exponential form, re to the I theta, where theta is the angle. So here, our angle is this part. That's our theta part. So you have here Z, R is 1.5 e to the I theta. Okay. And then for Z sub 2, this will be our theta. So R e to the I theta will be this part. Okay, so this one is complete. Hence or otherwise, find an equation for L in the form of this. So we already have this one. If we're going to combine these two together using these two complex functions, we're looking for, it says, you can write it in the form of, okay, imaginary C sub 1 sub 2. So when we are looking for the imaginary part of the complex number, then we're dealing with sign. Okay, so I think I have forgotten to write imaginary here of the whole thing. Okay, so this part, this, and this one. Okay, so plus d. We can factor out e to the 0.0093 ti, and then we will have this in the parentheses plus d. Let's just put the d later on. Let's just try to work on uh, the imaginary part. Now, this, what you can do here is to change it to rectangular format. So you type this in your GDC. Type the whole thing 1.5 e to the 2.83i minus 1.16, convert to rectangular. After that, convert your answer to polar. You will have this. Okay, this now gives you this answer in the form of r e to the I theta, where your r is this one, 3.06299 dot e theta I, oh, this one, I theta, 0.00939 t minus 0.2009, what is that, 2.9908661 plus d. Now, since you're looking only for the sine part, this serves as your, in the RCs, you're getting only the R and the I sine theta. So 3.06 sine, this is your theta, actually that's theta I, plus 12.65. This was the one we solved in letter G. Okay, so have we written it? Hence or otherwise, find an equation for L in the form of P sine theta. Okay, so our P is 3.06. Our Q is 0.00939. R is negative 2.99. And D is 12.65. Okay, just like this one. For part 3, find in hours the shortest time from sunrise to sunset at point A that is predicted by this model. Your model is this one. Minimum, the shortest is the minimum. Yeah, in a unit circle, the minimum for sine appears when you have here at 0, negative 1, right? So if we try to make this the whole thing minimum, have it negative 1, so we will have here 3.06 times negative 1 plus 12.65. Get your calculator and solve for this one. We will have around 9.42. That's the shortest time in hours. And then you can have, let's try to graph the whole thing. So if you graph it, the function given, the L of t, you will have the minimum point at 9.41751 or 9.42.